Ever wondered how technology could help you grow more rice with less guesswork? Let's dive in. Farmers, predicting your paddy yield just got a whole lot smarter. Using real data from 10,000 fields in Sri Lanka, machine learning models can now analyze everything from rainfall and temperature to soil nutrients, fertilizer, and even the type of paddy seed you use. We feed all these details, 17 different factors, into smart computer models with names like Random Forest and XGB Boost. They learn from past harvests and spot the hidden patterns that affect your yield. This means you get better advice on when to plant, how much fertilizer to use, and even which paddy variety fits your land best. The goal? Higher harvests, less waste, and smarter decisions for you and your community. Machine learning isn't just for scientists. Now it's helping farmers grow a better future, one field at a time.
Hi, my name is Jayathlete HRA. I will be presenting our work on using random forest algorithm for paddy prediction. Accurate paddy prediction is important for better planning in agriculture. For this project, we use data provided by the Batalaguna Rice Research and Development Center in Sri Lanka. The dataset includes 10,000 records and 17 different features such as rainfall, temperature, soil characteristics, and other environment factors that influence yield. We process the data by handling missing values and ensuring data consistency. Then, we split the data into training and testing sets using 80-20 ratio. Then, use a random forest algorithm, which is the enabled learning technique that builds up multiple decision trees and combine the outputs for more accurate and stable predictions. I created a correlation heat map to see how each feature is related to paddy yield. It shows that factors like area and rainfall have a stronger impact compared to others. Then, we identify 7 categorical features like soil type, irrigation type, water source, paddy variety, festivality, season, and district are separated from the numerical features. Then applied one-hot encoding to the categorical features while keeping the numerical features unchanged to prepare the data for model training. Build a pipeline that first pre-processes the data and then trains a random forest regressor with tuned parameters to improve accuracy and prevent overfitting. Then train the pipeline using the training data. When we consider about the training and test data performance, the training R squared is 0.9901 and testing R squared is 0.9731. This means the model performed very well. And the evaluation matrices of the model, the MA is 510.03 shows the average prediction error, and the MSE is 4.76 million indicating error magnitude, and the RMSE is 2180.69 offering a clear error measurement, and the R squared is 0.973 meaning the model explained 97.3% of the data's variance, and the mean absolute percentage error shows 3.5% average prediction error. And finally, the regression accuracy is 96.51% shows strong performance of the model. Test data and save the model. This is the permutation feature importance. When we consider about this farmer input and data predict harvest based on land size, this program allows farmers to input their land and environmental conditions and predict the total paddy harvest using a trade model. And it compares it with past yields and provide personalized recommendations to either improve or maintain the crop production. And when we talk about this visualization model performance, this scatter plot shows the most predicted yield closely match the actual yields along the ideal red line indicating good model performance. And when we consider about this residual plot, it shows the most errors are centered around 0, indicating that the model predictions are generally accurate. Thank you.
Hi, I am Pramadya Pumani. Let's walk through the crop yield prediction model developed using gradient boosting regressor. I chose gradient boosting regressor for crop yield prediction because of its strong ability to model complex, nonlinear relationships in data. GBR works by combining the predictions of multiple weak learners, typical decision trees, into a single powerful ensemble, which makes it highly effective for regression tasks like predicting agricultural yields. If we talk about the data preprocessing and feature engineering, before feeding the data into the model, I performed several preprocessing steps. These included handling missing values through imputation, lab encoding for categorical variables, and apply one-hot encoding where necessary. I use key features such as average temperature, rainfall, soil conditions, fertilizer usage, and paddy variety to give the model a comprehensive view of the yield influencing factors. If we talk about the model building and tuning, for the core model, I implement the gradient boosting regressor from scikit-learn. To enhance performance, I fine-tune hyperparameters using randomized search CV, which efficiently searches through the parameter space to find optimal settings. This helped reduce overfitting and improve the model's generalization. If we evaluate the performance of the model achieves an impressive R-squared score of 0.97, including a strong correlation between predicted and actual yields. It's also recorded a low mean absolute error, reflecting that the model's predictions were very close to the real-world values. I visualize the performance using scatter plot of predicted versus actual yield and a residual distribution plot, both confirming that the model performs well with the minimal bias and error. As a conclusion, the gradient boosting regressor proved to be a highly effective technique for crop yield predictions. Its robustness, ability to handle complex data, and strong predictive accuracy make it a powerful tool for supporting smart agriculture initiatives and informed farming decisions. Thank you.
Hi, I'm Amarisinghe AISA. Today I'll be demonstrate my crop yield prediction model where I have used light GBM algorithm, light gradient boosting machine due to its efficiency, scalability and high performance with structured data. I began importing a merged dataset that includes important features affecting paddy yield such as climate factors, soil properties, irrigation type, water source, pest severity, season, district. I use light GBM regressor with hyperparameters such as an estimator equal 200, learning rate equal 0.05, maximum depth is equal 4. These settings help balance model performance and avoid overfitting. After splitting the data into training and test, the model was trained on 8% of data. The model performed exceptionally well. Training R squared is 98.91%. Testing R squared is 97.68%. Mean absolute error is near 481. Squared error is near 4.1 million. I also calculate root mean squared error to access average prediction deviation, which adds more interpretability. Using a light GBMS built-in tool, I visualize the feature importance. It shows that rain, fertilizer usage, soil nutrition, and paddy variety had the highest impact yield prediction. In here, I created interactive input function where users can enter values like soil type, rainfall, temperature, district, so on. It predicts the harvest yield in kilogram per hectare and gives recommendation if the predicted yield is low than the previous year, such as improving irrigation or using high yield varieties like these recommendations. The scatter plots compares the actual versus the predicted yield. This is the feature importance. The residual plot helps the check for prediction errors. This correlation heat map shows how the numerical features related to the others. In summary, this light GBM based model is accurate, interpretable, and practical for supporting Sri Lankan farmers in making data driven decisions to improve their paddy harvest. Thank you.
Hi, I'm Chamandagar Nathlagan. Today we are exploring our XGBoost machine learning model that predicts rice crop yields that helping farmers optimize production through data-driven decisions. So when we talk about the model overview, our model uses XGBoost, an algorithm that builds decision trees sequentially, with each tree learning from previous cells. With 200 estimators and learning rate of 0.05 and maximum depth of 4, it's specially optimized for agricultural prediction challenges. So when we talk about the data preparation, we process agricultural data including soil properties, irrigation methods, and environmental factors, Likewise, so categorical variables like soil type and paddy variety are numerical encoded for fitting the database into training and test information. And after the training, we have the evaluation metrics. So in the evaluation metrics, we can see the performance like the model achieves robust performance with R squared of 0.9935 and test data it's 0.9753 and a mean of 460.79. This means the farmers can get an accurate prediction per hectare. So in the key visualization, especially when we talk about the correlation heat map, our correlation heat map reveals relationship between agricultural factors with minimum correlation, suggesting each feature contributes unique information. And when we talk about the feature importance, the feature importance not identifies as top feature as the most influential factor in yield prediction. Likewise, the features are followed up, giving farmers clear guidance on which variables to prioritize. In this actual was prediction plot, these scatters plot demonstrate strong alignment between predicted and actual data. This confirms the model's reliability across diverse growing conditions. And last testing one, you can see farmers can input their specific field conditions and instantly receive personalized yield forecasting along with targeted recommendation for improvements. And finally, by combining agricultural expertise with advanced machine learning, our XGBoost model brings bridges the gap between data science and practical farming, transforming the complex patterns into actionable insights for improved crop production. Thank you.